All right, so in the last lecture I showed you a few of the ways in which we have to debug MPI programs and how cumbersome that is. Now I want to show you how easy it is actually in deal.II. So what I would like to show you in this next lecture is how we use parallel computing with multiple processes, that is with MPI, in deal.II. And in particular, the canonical example that I would like to show you is step 40. There's a number of other programs that do similar things also with MPI. So step 32, which despite the fact that it has a lower number than 40, actually comes logically after 40. Steps 42, 48 are also there. There's an older style in which we programmed MPI in step 17 and 18, but this is not how we recommend anymore today how to use that. There is a whole documentation module on parallel computing with multiple processors using distributed memory. So if you want to find out what functions participate in this and how this all fits together, that is the place to go. And then if you want to see a little bit how the data structures and the algorithms that underlie all of the things that we implement in deal.II work together, how they're designed, there's a paper by myself, Carsten Borstede, Timo Heister, and Martin Kronbichler in ACM Transactions of Mathematical Software that you can find on my website as well. So when you want to deal with finite elements on, let's say, in parallel using MPI, what you would say, for example, is that all of the objects that participate in this, let's say the triangulation, the DOF handler, the constraints, the matrix, solution vectors, and so on and so forth, all of these things will have O of n memory at the very least, where n is the number of cells. And in practice, O of n is really all we can afford. So let's say I have a problem where I need 100 million cells. Then I need to store 100 million cells somewhere, and obviously I cannot do this on a single processor. So we have to split up every global object, the triangulation, the DOF handler, matrices, constraints, and so on. We have to split every single one of these objects up into onto the P processors that participate in this. So we will say that every processor holds O of n over P memory locations, or over n over P locally owned data elements of this. So if n is the total number of cells, 100 million, P is 1,000, then every processor would have to hold on the order of 100,000 cells. With a problem size of 100 million, it is quite obvious that no single processor can hold an entire global object, right? It is not possible that any processor holds the entire triangulation. As a matter of fact, it is quite obvious that no processor is even able to hold significantly more than 100 million by 1,000. That is 100,000 cells, right? So you cannot conceive of a scheme where, for example, the amount of data every processor has to store is not just n over p, but let's say a significant multiple, or even something that grows with n, right? So you cannot think, for example, that every processor is going to store n over p plus a small multiple of n, where the small multiple is independent of p. In practice, that means that we have to completely split up every one of these objects, that every single one stores n over p and not more than that. But we do need to sometimes store a little bit more. But this little bit more must be proportional to n over p. So for example, you could think of, let's say I'm storing the cells that contain that are part of the domain. Let's say my domain is a square. I store 1,000th of the elements on each one of the 1,000 processors. I can allow myself, for example, one layer of cells around it, right? That's something that is still proportional to n over p. And that is something that we sometimes need to do in order to implement algorithms efficiently, that I store a little bit of additional data, but it must be proportional to n over p. So in mathematical terms, I would say that I store O of n over p locally owned data and O of epsilon n over p ghost elements. Ghost elements are the ones that, for example, would be the rim around the domain. Further, the philosophy is that every processor may only work on the locally owned data, possibly including the ghost data as necessary. So, for example, that means that when we split the triangulation in such a way that every processor owns 100,000 cells, it can only work on the 100,000 cells plus possibly the ghost cells, but it can never try to work on cells that live somewhere else, right? Because we don't know about these cells. Remember, we cannot store the entire triangulation. We do not know about the other cells. We cannot work on them. We can also not request them because there would be too much data that is going back and forth. So deal.II is carefully written in such a way that it communicates data that may be necessary early on. So sometimes, let's say the ghost elements, we don't own them, but the triangulation makes sure that they're available locally. And then it tries to avoid further communication. For linear algebra, I showed you that we have our own linear algebra sublibrary. For parallel computation, that turns out to be really difficult. It is not trivial to write matrix and vector objects, and in particular solvers and preconditioners that work in parallel. And for these cases, we rely on libraries that are called PETSI or Trilinos. One of those comes out of the Oregon National Lab, the other one of Sandia National Labs. Both are national laboratories in the United States. These are high-quality libraries that do linear algebra and many other things as well in parallel using MPI, and they have been shown to scale to hundreds of thousands and millions of processors. So they're really, really good libraries for this purpose, and for what we want to do, we always build on them. So when we look at the deal.II programs, in deal.II itself, of course, there are places where we call MPI. In user programs, you almost never do this. You call deal.II classes, and internally they may communicate data as necessary, but by and large, the classes and the objects that you deal with are basically exactly the same as the ones that we've seen in steps 1 through 6, for example. So there's not very much explicit MPI communication that you have to do. I showed you how MPI works and how to debug MPI programs because these issues are still germane. You still need to understand when you call these deal.II objects how how communication works in order to understand why they're designed that way. For example, why can you not ask for cells that don't live locally? Well, because that would require communication, or it would require more data that you can store locally. And you may also happen into situations where you have a deadlock and you need to understand where that deadlock comes from, even if you haven't written that MPI call. You may simply be calling deal.II functions that internally do MPI, and you may be calling one of these functions on one processor but not in the other, and then you get into deadlocks just as I showed you with the second example of the previous lecture. So in practice, you don't write a lot of MPI code yourself, but you call MPI under the hood. I want to show you an example of how we split data. So here's a depiction of the triangulation that we have in deal.II that we use in, I think that comes actually out of the Step 40 tutorial program. So there is an abstract global triangulation of our domain, which is a square or rectangle here, where there are a set of finest cells. Okay, I forgot how many this is. This looks like a few thousand or maybe a few 10,000. So there is an abstract global triangulation, but we cannot access that global triangulation. Rather, every processor has its own object that stores the locally owned cells, then the ghost layer, and artificial cells then that we do not need to care about. So for example, processor 0, this is the domain, this is the square here. Processor 0 owns all of these magenta cells here, okay? And it has knowledge of one layer of ghost cells, including who owns these ghost cells. So you see that these cells are colored in green. These are the cells that processor 1 owns. There's a few yellow ones here. These are the cells that processor 2 owns. And out here, there is a set of cells that we call artificial. These are cells that are essentially just there to pad the domain so that every processor has knowledge of the entire domain, but it doesn't know all of the cells. So you see, for example, that processor 0 here has very coarse cells here, although the real mesh has rather fine cells over here. So processor 0 really only owns the cells here, and this is all that it knows. It does not know what the mesh looks like up here, because we cannot store this much, right? The object that does this in deal.II is called parallel distributed triangulation, and it is something that essentially offers a triangulation object on every processor, the union of which would correspond to this abstract global triangulation. On this triangulation, we would build a DOF handler, which has the same kind of structure. There is an abstract DOF handler that lives globally, but that is not accessible, that it is distributed among all of the processors. And each processor will build a DOF handler that is built on the locally owned cells. Now, one of the things that is important to understand is that so just like with cells, so we split the cells into the ones that we own on the current processor, we call these locally owned, and the ones that are not locally owned. Okay? Some of the ones that are not locally owned are ghost cells. For degrees of freedom, we need to have a finer distinction. In particular, we split all of the degrees of freedom into ones that we own locally. These are a subset of the ones that live on the cells that we own. But not all of the degrees of freedom that live on the cells that we own locally are in fact locally owned degrees of freedom. For example, you might have degrees of freedom that are defined on the edge between one of our cells and a neighboring cell. So for these degrees of freedom that live on this edge, you have to decide which processor is the owner. And it may be that we own it, in which case these degrees of freedom belong to the locally owned DOF set, or they may belong to the locally owned DOF set on another processor. Now, when you do local assembly, for example, you will compute matrix elements that belong or that correspond to all of the degrees of freedom that live on this locally owned cell. So we introduce a class of degrees of freedom that we call the locally active DOFs. It's not a class, it's a set. It's an index set. Okay, so the locally active degrees of freedom correspond to all of the degrees of freedom that live on the cells that we own locally. And it's a superset of the degrees of freedom that we own. Right? Some of the locally active degrees of freedom may lie on interfaces, may be owned by another processor. So that's what we call the locally active DOFs, and then there's a third class that we call the locally relevant DOFs. These are all of the degrees of freedom that live on the cells we own, plus the ones that live on the ghost cells. That's the one layer of cells around our own domain that we have knowledge locally. We oftentimes need these, for example, when you compute something like, so I should say this. The locally owned ones are the ones that correspond to the rows in the matrix and the elements of vectors that we store locally. The locally active DOFs are the ones for which we compute matrix and vector entries. And the locally relevant ones are the ones that we need, for example, to compute something like the difference between the gradient on one cell and the gradient on the current, let's say the gradient on a neighboring cell and the gradient on the current cell. That is something that we need for, let's say, the Kelly error estimator, where, let's say, we own a current cell, we want to know how large the error is, we need to compute the gradient here and the gradient on the neighbor cell. Well, the neighbor cell may, in fact, be a ghost cell. So we need to know the degrees of freedom and their values on the neighboring cell. These are exactly the locally relevant DOFs. That includes the locally owned ones, the locally active ones, plus the ones that are around on the ghost layer. With this, let us take a look at step 40. So step 40 is the parallel version of step 6. It computes just the Laplace equation, nothing spectacular, but it has been shown to scale to 16,000 processors, which today, or certainly when we wrote this paper in 2010 and 11, is quite a significant size. The differences to step 6 are surprisingly small. They're about 30 lines of code. And basically what it boils down to is that we need to let the system matrix and vectors know, and the constraints object, which are the locally owned and the locally relevant objects. Then we need to restrict assembly to the locally owned cells, and we need to create one output file per processor. And everything else happens automatically for you, so you don't really need to worry about this. But the point is that the differences between a parallel program and a sequential program, between step 40 and step 6, are actually not that large. Like I say, about 30 lines of code. It's more that you need to understand, let's say, how that actually works, what's going on there. So you need to have this conceptual model of, for example, locally owned, locally relevant degrees of freedom, or locally owned cells versus ghost cells, and so on and so forth. So with this, let me jump to the program. You can find the program in the usual location. You go to deal.II, you select the version, and so on and so forth, step 40.html. You can also go through all of the menus on the website, of course. We can run it as always. We go to the examples directory we call CMake, we run it, and then we're going to look at the output. So I'm just going to do this here. I had that somewhere. Here, yeah. So I'm going to go through the program. So as always, we want to start at the very bottom of this program. This is poorly formatted today. This is not what I had in mind. That looked better yesterday. Very interesting. Very interesting. I need to find out what is going on here. Anyway, so let me just show you the actual committed version of this in step 40. So view in large font. So the things that I usually show you is I start from the bottom, right? So I have my main function here, as always. I call the run function here, and so let us go to this run function. It looks exactly like before. You will find that there is basically no difference there. And the only things that I would like to point out to you is the changes that we've made to the setup system function and the assemble system function. So in setup system, because I couldn't show you the website, you will find that there's a lot of commentary in between, but I'll try to explain it to you anyway. So with the exception of timing output that I'm going to ignore for now, essentially what we do is we already have our triangulation that's of type parallel distributed triangulation. All we have to do is we have to distribute degrees of freedom, and that does a lot under the hood. So it would call, it would enumerate degrees of free locally, and then make sure that we have information about the degrees of freedom on ghost cells, and so on and so forth. So there's a lot of communication going on, but it's not important for you to understand that. Then the second part is here, where we have to get ourselves information about the locally owned degrees of freedom and the locally relevant degrees of freedom. So we store these in member variables. And let me show this to you. So essentially, the member variables of this, or let's say the entire class declaration of this class, looks exactly like in step 6, right? All of the same member functions. There's a DOF handler, there's a find element, there's a triangulation here now of this new type. The only new member variables that we have are these two index sets that essentially describe which degrees of freedom do we own locally and which of those are relevant locally. Okay, and then we have PETSI objects for the matrix vector, the solution vector, and the right-hand side. So when we go back to setup system here, here are the only significant differences. So when you compute the constraints that come from hanging nodes, the only difference really is the second one of these, the first one of these lines here. We have to let the constraint matrix know which are the elements, or which are the degrees of freedom for which we need to store constraints, and that these are exactly the locally relevant degrees of freedom. And then we do just like we always do. We compute the hanging node constraints. We compute the constraints due to boundary values. And then again, when we compute the sparsity pattern, then we need to look at which elements of the sparsity pattern do we actually need to know. These are the locally relevant degrees of freedom. Okay. And so we compute the local contribution to the sparsity pattern, and we need to do a little bit of communication. And then that's it. And then we can initialize the matrix with this. So that's really the fundamental changes. It's not very much. And the documentation of this tutorial program talks about this in more detail too. The second change is in assemble system. So in assemble system, we do exactly the same thing as we always do with one line addition. Namely, when we do this loop over all of the cells, we need to ask, is this a cell that we own locally, or is it not? So if it is not, it's a ghost cell or it's an artificial cell, then there's nothing for us to do. So every processor is going to assemble the matrix on its locally owned piece. And because the locally owned pieces, when you take them together, form the entire domain, we have covered all of the cells. Okay, so we only need to assemble on the locally owned part, and that's all we need to do. So with this one line addition, assemble system is exactly the same as it was before. All right. Then there are some changes in the solver because we need something that actually solves, let's say, on 1,000 processors or on 10,000 processors, and there's some technique or technology that needs to go in there. And then there are minor changes in refine grid, for example, that we need to call a function not in namespace grid refinement, but in namespace parallel distributed grid refinement. But basically, that's all it. In output results, what we do is we create one output file per processor. So we're going to call the solution solution dash and then the name of the refinement cycle dot the number of the subdomain on which we work. So the number of the subdomain is the number of the process on which we work. That's basically all there is to it. And so if I run this program, then I'm not going to show this to you, but if you run it, then what you get is a lot of output files. Okay, so I ran this earlier here on 16 processors. For example, when we come to the 7th mesh refinement cycle, there are going to be files from solution 07 0000 to 0015. So that's from the 16 processors that I ran it on. And then there's one file that we have also created that is called .pvtu. That's a file that we use for pair view that describes the individual .vtu files that participate in this simulation. So each one of these individual files only shows graphical output for part of the domain. But of course, we want the graphical output for the entire domain, and the pvtu file is one that ties it all together. Essentially, it lists all of the VTU files that belong to this one simulation. So if I were to visualize this with pair view, then what I get is I call pair view. I open, for example, let me say the solution-04.pvtu file. Okay. So I get this. Let me select the solution U. The solution U looks like this. It's not a particularly exciting case that we have here. I can, for example, show you the surface with edges. That is going to show you the mesh as well. Okay, so you see the solution, and we have chosen the right-hand side of the problem in such a way that it has a discontinuity along the sign-shaped line, and as a consequence, the solution is rough along that line, and the mesh refinement will always refine into this line. So you don't see this when you look at the at just the color plot. You don't see that there is a singularity in the solution, but let me assure you there is one. Okay, so this is the overall solution. This is the entire domain with the cells that participate in it. One of the things that I can do is I can visualize, instead of the solution, I also output the number of the subdomain. And now let me take away the edges here. So what you see is that each one of these colors corresponds to the cells that one processor owns. Okay, so this blue area here, for example, these are all the cells that processor 0 owns. And then here is probably processor 1 and processor 2, and processor 3 may have these two pieces here. And processor 4 has probably this piece and this piece. So you see that the pieces that each processor owns are not necessarily contiguous, but they're typically geographically fairly localized. Okay? And then all the way over to processor 16 over here. And you see that those processors that participate in the region where the mesh is fine typically have a smaller geometric area than the processors that have only coarse cells like 0 and 16, for example. So with this, you already have a way of playing with this. I would encourage you to look through the documentation of step 40 in a little bit more detail. But by and large, I think that the takeaway message is that there is not all that much that you actually have to change to go from a sequential program to a completely parallel program. That most of these things are handled by the deal.II classes under the hood, and that the places where you have to think, let's say, more is if there are no deal.II classes that do a particular task. Let's say if you have a special requirement that you, let's say, you want to advect particles through your domain. Well, there are times, of course, when a particle leaves the cells that are locally owned and enters the area that are owned by another processor. In a case like this, that's the time when you actually have to write actual MPI code when you hand off this data from one processor to another one. But if you just want to solve, let's say, a scalar or even a vector-valued partial differential equation the way you always do, the amount of code that you have to write in deal.II is not overwhelmingly large. Like I said, this program here has been shown to scale to 16,000 processors. It actually goes far beyond this. So if you look at the numerical results from this program, there are a number of plots here that show how this whole thing scales. So for example, here are a couple plots for a fixed number of processors. So let's say 256 processors. If I make the problem larger and larger and larger, the time that it takes this whole program to run grows almost exactly proportionally to the number of degrees of freedom I have. Similarly, if I have 4,096, if my problem is large enough, so over here to the right, everything grows nicely in parallel. So with this framework that we have in deal.II, you should be able to extend your programs in a not terribly difficult way to cases where you can use very large numbers of processors and scale well. That means to use them efficiently. With this, I would say go play with it, read through the documentation of step 40, and see how that is applicable to your own problems, and it should not be very hard to adapt your program with this. All right. With this, I think I will end the section on parallel computing, and like I said, there are documentation modules, there are tutorial programs that can take you from here.